Hey guys, Mr. Betts here. I want to take a look at another test that we can use to see if a series converges, and that's called the alternating series test. So, like some of the other tests we've seen, this alternating series test works on a very specific type of series. So, it's going to be kind of like a geometric series where it only works if it's a geometric series. This one's only going to work if a series is an alternating series. So, let's first talk about what an alternating series is. It's a pretty straightforward idea. Essentially, the idea is every other term is positive and every other term is negative. So this is one of many ways we could define an alternating series. And essentially what this is saying is if we have a series of only positive terms, then by multiplying those positive terms, alternating with positive 1 and negative 1, which is what's going to happen with that negative 1 to the nth power, then we get a series where every other term is positive, every other term is negative. Sometimes an alternating series is going to look like that. So in the first example I have here, that is exactly the form that this series is written in. So when n is positive, since n starts at 1 and goes up from there, any value that we put in for n, 2n over n squared plus 1 is always going to be positive. And then this negative 1 to the n, when n is an even power, negative 1 to an even power is positive 1. And when n is an odd power, negative 1 to an odd power is negative 1. So this is what's going to cause the series to alternate. In the second example here, that negative 1 is essentially multiplied into the meat of it. So this negative here is going to mean that this is always negative. But then when we raise that to a power, a negative to an even power is going to be positive, and a negative to an odd power is going to be negative. So again, we get that alternating form. This last one here isn't as obvious, but since cosine oscillates, if we take n and multiply it by pi, then what we're doing is we're taking the cosine of pi, the cosine of 2 pi, the cosine of 3 pi, and so on. So cosine of pi is negative 1, cosine of 2 pi is positive 1, cosine of 3 pi is negative 1, and that's going to bounce back and forth. So that's going to cause this series to be an alternating series, even though we don't have that negative 1 to the nth power that we can usually use to identify an alternating series. So this one's kind of disguised, but it is also an alternating series. So let's take a look at a particular alternating series. I chose this particular alternating series because it's also a geometric series, so we know a little bit about it from what we've done in the past. This geometric series in particular has a common ratio of negative 1/2, and the first term is 1. So that means that the sum of this geometric series is going to be 1 over 1 minus negative 1/2, which ends up being 2/3. So I chose this because we know, since it's a geometric series, that it's going to converge to 2/3. But I want to look at some features of this series because it's an alternating series. So first thing I want to do is take a look at partial sums, because that's how we define convergence for series. And you'll notice that the partial sums as we go across here are getting closer and closer to that expected 2/3 sum. If we look at the graph of the partial sums, some things kind of pop out to us. So you'll notice, because it's an alternating series, every other time that we go from one to the next, we've got a decreasing sum, and every other time the sum is going to increase. Okay, so that has to do with the nature of the alternating series itself. If we look at more specifically even versus odd, so I've got the odd partial sums in green and the even partial sums in red. The green partial sums, because not only are the terms alternating, but also the terms are getting smaller. So when I subtract and then I add, but the number I add is smaller than the number I subtracted, then what's happening here is my odd partial sums, which I have in green, are getting smaller and smaller and smaller. Okay, so if we look at those here, these odd partial sums are getting smaller, but they're all a little bit bigger than 2/3. If we look at the even partial sums, Actually, I'm sorry, I'm using even and odd backwards. You get the idea though. So if we look at the odd partial sums, which are all going to be under approximations or under 2/3, they're all getting bigger. And because the terms are getting smaller and smaller and smaller, so as we go here, the terms are getting smaller, then the gap between the over approximation and the next under approximation, or an under approximation and the next over approximation, that gap is getting smaller. So every other term is an over approximation, every other partial sum is an under approximation, and the over approximations and the under approximations are getting closer and closer and closer. So that means that what's happening here is the sum, which is 2/3, is getting squeezed in between those over approximations and the under approximations. So that gives us the alternating series test for convergence. One really important feature that I use there is that the terms were getting smaller. Okay, and that actually has to be the case because of the nth term test for divergence. If the terms aren't getting smaller and getting closer to zero, then we know right off the bat that it's not going to converge. Okay, so there are three conditions that have to be true for an alternating series to converge using the alternating series test. The first one is essentially just saying that it's an alternating series to begin with. So if a series is an alternating series, then condition one is met. Condition two says that the terms are getting smaller. So for every term, the term after it is closer to zero than the term before it. All right, so notice here that we're looking at u sub n and u sub n plus 1. Those are the positive terms. Okay, so that's what we call an absolute series because all the terms are positive. And each one, the next term is smaller than the term before it. We can usually show this using some sort of inequality, looking at the terms themselves, and we'll look at this with some examples later on. Just because the terms are getting smaller doesn't mean that they're approaching zero. We could have a series that the terms are getting smaller, but they're getting closer to like 2 or 1. For a series to converge, we know that the terms have to approach zero. This third condition should be met if we're even considering it to be convergent, because we know that if that limit is not zero, the series is going to diverge by the nth term test for divergence. So the justification that we're going to use and what we need to show that a series converges using this alternating series is what I have written down here in blue. So we're going to say the alternating series, so that's condition one, converges by the alternating series test. So that's what we're using because the terms decrease. So decrease is condition two in magnitude. So magnitude is just looking at the absolute value of the terms to zero. So that's saying the limit of the terms is approaching zero.